Okay, good afternoon everyone, and welcome to the last session for today's Gyan program. And thank you very much for your attention and for your attentiveness. So today's last program, actually the session is focusing on instrumentation for subdermal and epidermal wearable devices. So we have been hearing about different kind of sensors: subdermal sensors, epidermal sensors, non-invasive, minimally invasive. So there is always all these sensors. When you look at an application, it's not just a single expertise which is required. It is actually an interdisciplinary problem, and it consists of it requires multiple skills, involvement of multiple people at different stages of the developmental phase, research phase and development phase. So today's session actually is the goal of today's session is to provide you with the basic knowledge, irrespective of whatever background you come from, whether you are a chemist or an electronics engineer or whether you are a biotechnologist. At some point, if you are interested in sensor development, the session today will help you understand the basics of instrumentation that is involved. So you won't feel lost. You can at least guide people if you have members in your team. Using this knowledge, it will be helpful for you to, you can speak to an electronics engineer, explain your problem to them better. If you are collaborating with someone, you can even develop it yourself. This instrumentation for sensing is not very complex, so you can also learn on your own as well. So we'll have a look at these. What are the instrumentation methods that are used for different kind of devices? So if you look at the typical method by which doctors actually diagnose a disease, so they look at the vitals and then they look at the biomarkers. So the first evaluation phase of a patient is to look at their vitals. So there are many different types of vitals. Let's say ECG, heart rate, blood pressure, SpO2, respiration rate, EEG. So these are different kinds of vitals that ideally are monitored in a non-invasive manner. Okay, and then these vitals are somehow, there is a link between the biochemicals and the vitals. Okay, so if doctors find that there are some abnormalities in the vitals, that is the first stage of diagnosis, then they would advise you to look at the biochemicals. So they might advise you a blood test, or they might ask you to monitor a certain biomarker. They might ask you to check for certain metabolites, proteins, pH, like many different types of markers are there, which actually indicate or help the doctor understand why a certain vital is having some problem. So why there is any abnormality in the vitals. So this review actually written by Kuldeep Mahato, and he is actually part of this group by Joe Wang's group. So they are based in UCLA. So if you are interested in sensors, then in addition to our expert Professor Sanjeev Sharma, they are one of the other groups to follow their work. And the good thing about this review is they have nicely actually presented the vitals, biochemicals and all the different kind of sensors that are required for it. So you have glucose, lactate, cortisol. These are some biochemicals that are typically monitored, and all these markers they can be monitored continuously, and they have some use case for continuous monitoring of these markers. Okay. So they have all these markers. There is a user case. There is a justification to monitor all these markers continuously. So there are many markers. There are many biochemicals which do not require continuous monitoring. A spot test is enough. But these are certain markers for which continuous monitoring is required. Hence, we have to if continuous monitoring is required, then we have some justification to develop a wearable device. If it's just for a spot point of care device, then we don't have to think about continuous monitoring. So moving on, so as we have looked at, so this actually is the epidermal sensors that Sanjeev sir previously explained. So this is actually epidermal sensing, microneedle based sensors. These are subdermal sensors. These are subdermal sensors, which are actually, you can see the needle actually goes up to the dermis at max. It's not penetrating into the hypodermis. So it remains somewhere in the epidermis and the dermis. Okay, and the depth is around 1.3 millimeters. So the thick of the dermis. So your needle would be at least less than 1 millimeter in length, to penetrate the dermis. Okay. So that's how, and I also learned in this in our in the GYAN program, during the course of this GYAN program. So the tip diameter for good penetration, for the tip diameter, ideally, do you remember what it is? Very good. So it is around 20 microns or 20 micrometers. So if it is around that, then the penetration is smooth and painless almost. And then you see that what happens is here, as Professor Sanjeev was previously explaining, as the needle is inserted, the interstitial layer, the fluid, it forms a layer around the microneedle, and then you can start sensing. So that is why we have this you can say sensor start time, that one you cannot do immediately. You cannot, it's advisable not to start sensing immediately. Once you insert the sensor, you allow the sensor to stay there for some time, allow the layer to form, and then you start sensing. Then you will have a much more reliable and a better result. So this is the case also in CGM sensors. Today we will show you some CGM sensors as well, where you, once you implant the sensor, up to 1 hour you will not be able to get any reading out of the CGM sensor. So that is the sensor warm up time or startup time. So this is your minimally invasive subdermal sensing. So this again is another interesting technique which is non-invasive. Okay. Unlike optical methods which require very difficult or complex instrumentation for spectroscopy and all that, this requires a very simple approach which we call as reverse iontophoresis. Reverse iontophoresis. So in reverse iontophoresis, we apply an electric field, plus and minus, and this electric field actually creates a flow of ions, sodium and chloride ions. So whatever ions that are present inside the interstitial fluid, they start moving towards the electrode because of the electric field. Now when they start moving towards the electrode, what happens here is, you can actually, what people have demonstrated is, you can also monitor non-charged or neutral molecules like glucose. It does not have any charge on it, but when the ions are moving, they are actually hitting the glucose molecules, and it causes the glucose molecule to come out of the skin, and then you can monitor them. Okay. So this was the concept that was present in Gluco watch. There was a device called Gluco watch, which was commercialized, and then gradually it was released. It was pulled back again. It was not used because of many issues. You can look into that. So one of the issues was it had a very high MARD, mean absolute relative difference, between the blood glucose and the reading that it was giving. Then there were some reactions, if you continuously extract current, so there are some reactions with the skin, so irritation might be there. So that's why it was withdrawn. However, this is an interesting technique where you can have small devices, unlike like Professor Prasoon was saying earlier. Optical device was very large, using the analogy of a bottle. So this, using a reverse iontophoresis, you can have a very small device, as well as if you play around with the way you are extracting the fluid, then you might be able to overcome certain disadvantages that are generally associated with reverse iontophoresis. Anyway, so here this is, if you look at the fourth picture here, you see this actually shows the capillary endothelial cells, and it tells us that molecules which are of very small size, they easily leak out of the capillaries and in the capillary blood flows. So they leak out into the interstitial fluid. So these are the molecules that we can easily monitor: ions, glucose, lactate, cortisol, levodopa, insulin, which is slightly larger, antibodies, even antibodies also, and then you have the inflammatory biomarkers which are large in size, but still under certain circumstances you can also monitor them. So now coming to the next phase, once you have the so we know that we are actually monitoring from the interstitial fluid, or using reverse iontophoresis to extract the interstitial fluid. So now actually what are the analytes that we are interested in, and what electrochemical method we can use. So electrochemical methods are cheap to implement, they are not very expensive to implement. That's why, and you can also compress them. You can make it into a small chip, electronic chip, and you can easily actually miniaturize them. So that's why you have the so what are the electrochemical sensing modalities? For sodium, generally we use potentiometry. So all sorts of, we can use ion selective electrodes, ISE, which has an ionophore layer on the electrode, and they allows only selectively certain ions to pass through and they block the other ions. So these are ISEs. pH also you can monitor. So we'll look at pH today and also in the live demo. So glucose, these actually use a chronoamperometry, lactate also, and then ethanol, which is alcohol actually. So they use various enzymatic methods which we have already covered in detail. Enzymatic methods, and you can also have non-enzymatic methods also, but for stability these enzymatic methods are quite stable and repeatable, so that's why people tend to use them more. And then you have other markers such as uric acid cyclic voltammetry, then square wave stripping voltammetry and all these things. So if you want to do, let's say, a label free detection, then you can also use EIS, electrochemical impedance spectroscopy, where if when the target analyte sticks on the surface, the impedance of the electrode changes, and you can use that as a measure of concentration depending upon the impedance. So you can actually, so this table actually summarizes what is my analyte and what is the method to detect it. So it's a nice link between them. So let's say you want to implement a sodium sensor, then you would go for potentiometry, unless you want to develop your own method, of course. But the traditional method is potentiometry. So similarly for glucose, generally people use chronoamperometry. So in this way, there is a link between the analytes that I want to monitor and what is the sensing modality. Okay, now as engineers and scientists, we deal with complex problems. So in order to solve a complex problem, what we try to do is we try to break down that complex problem in very simple steps. So that is what we are showing here. So it's like a block diagram, or step by step process where we can go from development to deployment. Okay, so what are the steps? First is the design phase. So here you design your sensor, you look at the material properties, you look at the transducing mechanisms. So if you are doing some sort of maybe let's say you want to implement flexible sensors, what should be the material properties, what is the Young's modulus that you require for your material, and all these things come into the design phase, where you actually focus on sensor design. So here you might we require the electrochemistry experience, and we also require material scientists. So all these different kind of experience are required at the design phase. And then after we have designed the sensor, we look at the sensitivity, selectivity, stability. So today Professor Sanjeev in the morning he showed you different you can see parameters which are actually required to validate a sensor, how good your sensor is. So these are the parameters: sensitivity, selectivity, stability. Then we have MARD, mean absolute relative difference. So this we will look in more in detail at later lectures, where we are using AI to actually improve the MARD. And then we have the dynamic response. Dynamic response means how fast a sensor responds. Let's say in the body the analyte, let's say glucose is changing, let's say within 1 minute it is going from X to Y, whether your sensor is responding as fast or not. So that is the dynamic response. So that is so you are not only, because you are doing it for continuous monitoring, you are not only doing spot measurements, you also want to do the dynamic response. So if let's say I am moving from X to Y milligrams per deciliter, so whether your sensor is responding at the same rate or whether it is slow to respond, that is what we call as dynamic response. Okay. Now once the design phase is complete, we move to manufacture. So this is where actually this design phase is very important, because all the subsequent steps, they are actually in a way implemented in the design phase. So whenever we are designing a sensor, if we want to take it to market, then we want to have a process which is scalable. So ideally we want to when we take it to factories to manufacture, they already have their own manufacturing processes. The more similar to that manufacturing process, the better it is for us. Okay. So all these considerations, like in addition to sensor properties, we want to make the device scalable. Scalable means we can go from small volume to very large volumes easily. So that is what is being considered at the manufacturing phase. And here we do device to device variation. We check if we manufacture, let's say 100 devices, what is the variation that you see across devices. Ideally we want to minimize the variation. So this is in the manufacturing phase. And then we have large scale testing. So once we have manufactured the device, we want to actually validate it. So this is where you might have clinical trials, large clinical trials. Okay. And then clinical trials have different phases, the safety phase 0, phase 1, phase 2, phase 3, like this many different phases are there. So, all of this comes under validation, and once we are happy with the validation, the final stage is deployment. Okay. So, deployment is another, you can say it's an unknown step. We do not know whether once it goes out into the field, when we are using it in the lab, we know, okay, we should use it in a such and such manner. So, now you can provide this advice. Let us say you ask the user to wear it properly on the, so you ask the user to implant it on the, let us say on the back of the arm. Maybe the user is not very attentive, so they might implant it somewhere else, and then the sensor is not working. So, there are many factors which and unknown aspects which are there in deployment. So, once the manufacturers, they actually take feedback from the users, and then they, if required, they go back to the drawing board, and if necessary, they actually release another version of the sensor. So, all of this, and when doing this another second version of the sensor, they might improve the sensing layer ability or sensor capability, or they might also want to change the instrumentation that goes inside the sensor, depending upon user feedback. But broadly, these are the 4 different steps: design, manufacture, validation, deployment. Right. Since we are all working in sensors, let us see what is the roadmap, where the industry is heading, where we are going. So, what is the next step? So, here we are in sensors 3.0. So, the next step is sensors 4.0. Okay. So, what we want is, we want AI on sensors. So, nowadays most of the AI is present in the cloud. So, you have the cloud where sensor data is going, and then you are using AI models to process, train, and then deploying it back to the mobile or edge device. But ideally what we want, for data security reasons, the AI to be present on the edge, on the device itself. So, this is the next step, where we call it as connected intelligence or sensors 4.0, and that is where we want to develop AI models that can be squeezed in small platforms, right. So, that is what we call as, once you squeeze AI on the sensor, we call it as intelligent biosensors. Simple thing. Okay. So, like I told you, as engineers, we try to break it down into different steps. So, we have actually developed a technology stack. So, what are the different technology requirements in an intelligent biosensor? So, the first stack is this one. So, it is just an easy way to understand. The first stack is the microneedle fabrication. Okay. So, that comes under the first technology stack or layer. Okay. So, then we have already looked at various fabrication methods. Professor Sanjeev has already developed and explained to you in previous lectures how to develop microneedles. Then we have, so we have the microneedle array, and then we have the sensing layer, that also comes in the first stack, where many different methods are there. You can use an enzymatic method, you can use plastic antibody, which is quite interesting, which we learnt earlier. So, many different sensing methods are there, and this sensing method or layer is dependent on the analyte that you are actually trying to monitor. Okay. So, all this comes under stack 1, and then as we insert the sensor into the body reacts. So, we need an anti-fouling layer. So, there are many different anti-fouling layers that are present that can be used on top of your sensing layer. These anti-fouling layers have to be porous as well, so that they allow the analytes to pass through. And then on top of the second stack is actually the instrumentation. So, this is what we are actually looking at today, right now, in the current session, which is the instrumentation. So, this is the current session that we are looking at. So, in the instrumentation, we will have amplifiers. So, if you do not understand amplifiers, there is no need to panic or be scared. They are very simple and easy to understand, and I hope by the end of the session you will be able to understand it properly. So, amplifiers, you might have analog filters, you might have filters, and then you might have something called as ADCs, analog to digital converters. Okay. Analog to digital converters. Now, once your sensor is, so this will actually convert your current that is coming out of the sensor or voltage that is coming out of the sensor into a digital series of bits. Okay. So, that is the language that is understood by computers. So, we all talk in analog, but the computer understands in digital. So, even this microphone has a digitized an ADC which converts voice, which is analog, into digital. Similarly, sensor signals are all analog, current, voltage, continuous signals, they are digitized into digital bits. So once it is digitized, the next step is to, we can take that data to the cloud or to the mobile phone, wherever we want. So that's why we need some sort of a communication protocol. You can have Bluetooth. So that is your second stack, the instrumentation. So the first stack is the sensor, then you have the instrumentation, and then since we want a connected system, we have the third stack, which consists of the decision making algorithm. And this decision making algorithm, there are many different ways to do the decision making. You can use control based algorithm, or you can also use AI nowadays. And then whatever decision, whatever output you require, I'll give you some examples. So that decision is actually can be given to an actuator. So actuator is like an insulin pump. So insulin pump is an actuator. So let's say I am monitoring glucose. The sensor is collecting my glucose data, processing it, and let's say the AI says that okay, I need to inject glucose. Then this information goes to the actuator or the insulin pump, and then this is again given back to the body. So if you focus here, so there is a closed loop system here. You see from the body, so it goes like this, and then it comes back. Okay, so you are the start of the loop is the glucose level sensor, and then you have the decision making, and then insulin which again affects the glucose. So it's a closed loop system. Okay, so that is what we call as a closed loop system. So that is the third stack, and the fourth stack is data storage. You can store it in the cloud. You can actually do the AI on the cloud as well. It's up to you, depending upon what type of AI you are using and what type of hardware you are having. So this is the fourth stack. Okay, so these are stacks. So in an intelligent biosensor, you would have 4 different technology stack, and this stack is meant to simplify things, help you understand and identify which area you can contribute. So let's say my expertise is more on the electronics and AI side, then I would like to work in let's say stack 2 or stack 3. So I would need help from stack 1. So I can collaborate with someone who has more knowledge in stack 1. Okay, so this is a way to simplify methods. So this is a typical closed loop system. We call it as artificial pancreas, where you have it starts with the sensing. So this is my first step. Then the control algorithm, which controls the actuator, and then again it goes back to the glucose level. So that is how, and this is my CGM sensor. So these are the old CGM sensors, which are actually Empatica CGM sensors. They used to be on the waist, and nowadays CGM sensors are located on the arm. And this is the insulin pump. This is the insulin pump. So the insulin pump is still being used like this, but the CGM sensor has moved from the waist to the arm, maybe due to tolerability and comfort reasons. People have moved it. And also one more thing to note here is there are certain devices in the market which actually combine sensing plus actuating. So you have both the sensor and the actuator in the same single device. So you will be wearing a single device, small device on the arm, which will have the sensor as well as the actuator. So there are certain devices also like that. One more thing to note here is one of the reasons why people keep it separate is, insulin has limited supply. So people need to replace the insulin cartridge, you can say, or the injection. So once it finishes, they replace it new. So when you have it in a single device, I don't know, I'm not sure how it works out. So this is the solution that we have generally. So that's an insulin pump, very small. It's like a credit card, credit card or debit card size. And then you have the sensor here. So this sensor actually, it goes, it's a long one. It's actually subdermal, right? Yeah, subcutaneous. Sorry, subcutaneous. So it's not subdermal. So it's subcutaneous. Subcutaneous means it penetrates the dermis and goes deep into the skin. That's why you see this is the sensing needle. This is not actually a needle. It's a flexible polymer substrate. So they use a device to puncture the skin insert the sensor and take it out. We will show it in the lab also in the during the hands-on session. This is the current solution. So this is a much more better way to understand how the interstitial fluid works. So you have the this is the layer of the skin. You have the epidermis, dermis, and the subcutaneous layer. So this is where the CGM sensor would go up to the subcutaneous layer. Microneedles go up to here. So these are the microneedles. Okay, and then because when you go deep into the subcutaneous layer, you might encounter some blood capillaries, and when you are actually removing the sensor, sometimes you might have some blood which might come out because they are actually subcutaneous. So, and this is actually showing the diffusion from capillary to the interstitial fluid, the fluid flow, and these are so the diffusion actually is dependent on the size of the analyte, small, medium, large size. There are different sizes of the analytes which are actually you can detect. So up to 7 kilodalton you can easily detect. Is it clear? Right. So a much more detailed way. So the much more detailed diagram here. So you can see here these are the analyte sizes. So here we have free paracellular diffusion for small molecules like ions, glucose, urea, cortisol, vancomycin. Sorry, ions, glucose, urea, vancomycin, cortisol. If you want to monitor, let's say, insulin, so this comes in under medium solute. So this is actually something we call it as transitioning. So moving from paracellular diffusion, and as the size of the analyte increases, the diffusion actually becomes harder and harder and harder. Okay. So during inflammation, if the epithelial endothelial layers are actually become larger, the gaps between them, so they can actually diffuse easier, but that is only during inflammation, some sort of inflammation. So if that happens, you can actually detect this is an inflammatory marker, IgM, IgM. So it's around 990 kilodalton, so very large size molecule. Right. So one more thing to keep in mind, since we are working on the engineering side also. So when there is diffusion from the capillary into the interstitial fluid, it's actually, you can actually model them as a first order differential equation, and when you do that, there is a delay. So there is actually a delay, physiological delay that happens. So there is a delay if blood actually, let's say at 4 p.m. your glucose is spiking in the blood. So this delay will cause the spike in glucose to be detected around 10 minutes later. So there is a delay. So there is a physiological delay. So that is why we use AI to forecast the glucose level in advance, so that there is no problem with dosing and other things. We use some data processing methods to forecast the delay in advance. So these data processing methods we will look at a later lecture, but that is why we need some sort of a data processing approach to account for this delay. And this delay happens because of diffusion dynamics between the capillary and the interstitial fluid. Right, gradually we are moving more and more towards the engineering side. So as I told you, it's about breaking down the complexity into simpler block diagrams, easier to understand. So we have the biosensing element here, okay. Then we have the transducer, and then the transducer through the, let's say we are doing potentiometry or amperometry, it will generate an electrical signal which we are going to detect. So the first method that we have seen up to now, so it is, let's say we are doing glucose detection. The signal to be measured is actually a current. Okay. So this is actually measured. So we have 3 electrodes: the working electrode, reference electrode, and counter electrode. So what we do is, in amperometry, we apply a fixed potential between the working and the reference electrode, and we measure the current that is flowing through the counter electrode. Okay. So when we apply this constant voltage, redox reaction happens, and whatever ion exchange takes place, that is actually detected through the counter electrode. Okay. So that's why we say current at fixed potential. Now in potentiometry, we do not apply any voltage. We simply measure the voltage between the working electrode and the reference electrode. Okay. There is no flow of current between working and reference electrode. Okay. So then we can measure we simply measure the voltage between the working electrode and the reference electrode. This is for potentiometry. So in voltammetry, what we do is, generally it's used for heavy metal detection. So what we do is we do a potential sweep. So this voltage that we are keeping constant, between the working and the reference electrode. So, it is no longer constant. You can use some sort of a sweep, so triangular waveform, which you can actually use to change the potential and then look at the current that is coming out, and you can do your analysis. And then there are some sensors which are impedimentric. So, we look at change in impedance. So, these are level free sensing, and generally surface binding happens in impedimentric sensor, which causes the sensor to change the surface impedance, and then we are able to detect it. Okay. So, there are other types of sensors which we are not going to discuss, which is conductometric and capacitive sensors. Most of the touch screens, they are capacitive sensors. Okay. So far so good. Moving on, so I just wanted to give you a feel of how the glucose sensor looks like. We also have some samples. So, these are the typical glucose sensors. We have the Guardian sensor from Medtronic, Abbott Freestyle Libre sensor. This is the sensor which we have in our lab and which we will demonstrate also during our hands-on session. If you wish, you can also implant it. And then we have, if you wish, I want to say, there is no, we are going to implant ourselves, but you don't, it's up to you if you want to try out. So, then we have the Dexcom G6 sensor. So, these are the big players in the glucose sensing CGM market, so to say. And we have already looked at these things, so I don't need to go in detail. The first generation, second generation and third generation sensors we have discussed in detail previously. So, all of this actually use enzymatic sensing. So, now coming to the artificial pancreas, so we will mostly be looking at the glucose sensor and how we can extract the glucose signal here, glucose concentration. That is our main focus of the lecture here today. Glucose concentration, how we can actually, what kind of instrumentation we require to measure the glucose concentration. So, that is what we will be mostly focusing on. So, overall I just wanted to give you a feel of how the entire system looks like. So, the entire system, this is a way to model the entire closed loop system where you have the controller. This is the, you can say this is the algorithm, the AI model or algorithm, which is like a controller. Okay. And then which controls the insulin pump, and the AI algorithm is dependent on this signal here. So, this is the control objective. Let us say I want to maintain my glucose level within a certain range. So, that is the objective, that is my range in which I need to control the glucose, and this is whatever signal is coming in. So, it finds out the error, it calculates the error difference between the objective and the real term value, and then accordingly the controller will generate a signal U, which will actually control the insulin pump and try to bring it down within that same range. Okay. And this is how you can actually model in an individual with type 1 diabetes. So, there are many different in silico models of type 1 diabetes. So, UVA Padova model is a very popular model, that in silico model, UVA Padova. So, it is developed by University of Virginia and Padova University, which is in Italy, and this model is actually FDA approved. So, let us say you want to develop some AI models and you want to try out some things without collecting actual data, then if you show the UVA Padova model, if you use the UVA Padova model to generate some patient data and you can test your AI quickly on that. Of course, the holy grail is actually the clinical data, but you can start with the in silico data without having to wait for the clinical data. Okay. So, there are many different approaches. So, this controller, we can use it as a PID control, that was the old way in which how people used to do. Then we have the bio-inspired modeling, beta cells, and recently people started using the deep learning approaches. So, this deep learning approach we will look more in detail in a later lecture that is going to come. So, generally, okay, so now coming more and more towards the instrumentation side. So, amperometry is used for glucose sensing. In amperometry, actually, as I have already told you, you maintain a constant voltage between the reference electrode and the working electrode, and then whatever current that is being generated in the reaction, we try to measure using the counter electrode. Okay. So, this is the amplifier that we have here. So, I will show you some front ends that we can use. So, you have the reference electrode. So, this voltage actually appears here. These are so this will again be VDD by 2, and this is the counter electrode through which you are actually measuring the current. So, if you look at the voltage between working electrode and reference electrode is actually 0.65 volt. Okay, the difference, voltage difference. So, this could be the oxidation potential that you require to start the redox reaction, and then you measure the current that flows through the counter electrode. Now, in the olden days, previously, let's say we did not have any electrochemical sensing front end. So let's say I want to if you think of an engineering project, let's say during your BTech days, early BTech, first year, second year, you might be doing a project where let's say there is a sensor which will detect, let's say, movement and turn on the light. So one of the components that is required is a microcontroller. So the microcontroller will detect the movement and then it will turn on the light, right? So we did not have this kind of application or this kind of, let's say, device in electrochemistry. Okay. So if you want to develop a sensor, you have to have a potentiostat that you have to buy, which is a big device, and you have to use it. But in recently, around, I would say, let's say 2022, 23, around that time, analog devices, they have released this chip. So this AD5940 or AD5941. So this chip actually, if you can bring that. So this chip actually you can use to do you can make your own potentiostat. So you don't have to actually if you wish, you can also make a much more smaller potentiostat. So this is a evaluation board of AD5940. It has a chip, AD5940 chip, and this actually has the functionality of a potentiostat. Okay. So you can actually make your own, if you want, you can make your own potentiostat using this chip. So you don't have to worry about how will I implement amperometry, how will I implement potentiometry. All the functions are already there in this chip, AD5940 or AD5941. Okay, and it has a very comprehensive and detailed data sheet that you can follow, and there are many examples on their website as well. So you don't have to program it yourselves. You can use these examples, and then if you want to modify according to your need, you can modify the program. Okay, so we look into this a little bit more in detail later on. And this chip size is very small. So this is in millimeters, as you can see. So the size is, you can say, 3x4, very small, 3x4 millimeter. It's very small, 3.6 cross 4.6 or 4.2. So it's a very small form factor chip that we have, and all you need to do is you need to design your own PCB, and there are many more tutorials that are available to help you design your own PCB. But once you do it, you can easily have your own potentiostat. You don't have to rely. Let's say I am developing a wearable device where I need to develop a potentiostat, or where I need to use a potentiostat for any marker. I don't have to have a bulky potentiostat that is present in the lab. I can design a small one using AD5940. This is called as an evaluation board. I'll talk about it. But the chip itself is very small, so you can have your own PCB, much more smaller form factor, and you can have your own CGM sensor using this front end. So this front end, analog front end, was not present previously a few years back, and we had to design our own front ends, own amplifiers and everything. So I'll show you, I'll give you a flavor of the old approach and also the new approach using this one. So this is a chip which one of my previous colleague, she actually made, Sarah. So you can see here there are many different components here. The reason I wanted to show you is there's some few things which I wanted to actually explain. So this is your potentiostat, and then you have the ADC. Okay, so this is the analog to digital converter. SPI stands for serial peripheral interface. So this is another interface that you can use to extract digital bits serially out of the hardware, out of the, let's say you have this AD5940. If you want to extract some digital bits out of it, then you can use the SPI protocol. Okay, so we all are familiar with USB. So USB is one of the communication protocols. Similarly, SPI is another communication protocol. So both of them are serial. Okay, so USB stands for Universal Serial Bus. This is again a serial protocol, SPI, serial peripheral interface. Okay, so using this you can actually extract data out of it. But previously this design used to be done entirely customized. So this is the counter electrode, and the red arrow shows the direction of current. It flows inside the potentiostat, going inside this triangle here. and this triangle has some electronics internally, some transistors which measures the current, and then you measure what is your concentration. So I'll show you an example of this. This is a much more detailed diagram of the previous chip. So the chip actually, this is called as an ASIC, application specific integrated circuit, ASIC, application specific integrated circuit, integrated. So this is called as an ASIC. Let's say I have an application for sensing, then I would design an ASIC. Now this ASIC design process is a very tedious and long process. Okay, so at least it takes 1 year to design a chip, have it fabricated, bring it back to your lab, test it. Okay, so it's a long process. So generally in wearable medical devices we have two trade-offs. Trade-off means we have to think of majorly two aspects that we need to look at. One is called as power and the other one is size. Okay. So if your device is consuming a lot of power, that means you need to have a big battery on it, a large battery. So then your device size increases. So if you are actually increasing the power, device size will also increase. Ideally we want something which is low power and small device size. So this is where actually you can do some intelligent or many clever techniques that you can apply in your ASIC to ensure that your device is small size and low power consumption. Okay. So that is where actually, so that requirement, previously the requirement for ASIC was there in electrochemistry because there was no available platform. So nowadays we have a platform which is AD5941 or AD5940. So we do not require an ASIC per se. Okay. Only if I want to, let's say this chip has a certain power consumption and I want to have lower power consumption, then ASIC design is required. If I am not too much worried about the power consumption or the if I don't have any justification for going smaller chip size, then I can use AD5940. It's easy to program, easy to use, I can buy off the shelf, I don't have to actually worry about these things. Okay. So this is a much more detailed block diagram of the AD5940 where you have the current channels. So current channels, what type of electrochemical method uses current, generates current? Amperometry, very good. So it is actually amperometry. Okay. So these current channels, if we look in much more in detail, so they have something called as a TIA amplifier, trans impedance amplifier, which will convert amperometry into voltage, and this voltage is actually digitized using ADCs. So using ADCs, these ones, sorry, these ADCs actually digitize the output from the current channels. Voltage, potentiometry, okay, potentiometry. And then we also have impedance, for impedance measurement, EIS. So it's a nice chip with lot of different, almost all functionalities, modalities packaged within a small chip. So it's good to remember this chip AD5940 or AD5941. So if you are developing wearable sensors and you don't want to do ASIC design, or you don't have the, so this ASIC design requires in-depth knowledge of electronics. So if you don't want to do that, then you can go for AD5940, AD5941, and this is the evaluation board of the chip. So generally what happens is, let's say I want to test, this requires some programming. Okay. So if I want to program the chip and test it and use it without having to develop my own PCB, then I can use this chip, this AD5941 or AD5940 evaluation board. These are my electrodes that are required, reference electrode, working electrode, all the electrodes that are needed for electrochemical sensing. I can insert it, I can program it, I can test it. Okay, once I am happy with the program, once I am happy with the application, then I can design my own PCB with the same chip. So I just need to transfer the program into the chip. So I don't have to do the programming again. So in that way, so that is the typical design phase. That is where you use the evaluation board to test the whole process. A much more in-depth diagram. I don't think we require to go into all these things, all the details. If you wish, we can discuss it at a later stage. But this is the AD5940, fantastic chip, very useful. So this is the block that we generally use for amperometry, for sensing the current let's say out of a glucose sensor or a lactate sensor. Clear? Okay, I just wanted to highlight also. So this is actually I just wanted to show you how it has been used in a platform. So this is a paper recently published by the same group, I think Joe Wang, where we have multi-analyte sensing. So multiple sensors are implemented. So they also have a microneedle based platform, which is this one. It has a microneedle sensor patch. So I think they had glucose, and then you have lactate, and then alcohol. So these are few analytes they were trying to monitor at the same time using the same platform. So within the same microneedle platform, they have these multiple sensors that are implemented, and they use this AD5941 or successfully, and they have demonstrated this. So this was published in Nature Biomedical Engineering, and yeah. So this device is detachable. So the electronics itself you don't need to throw. So let's say you are using a sensor. You can use the sensor for a limited amount of time. You cannot use it infinitely or for a very long amount of time. So you can use it, say, let's say for 1 week or 2 weeks, and then you have to throw away the sensor. So instead of throwing away the electronics, you can simply detach the array, throw it away, and replace it with a new array. So that's what they have actually shown here. And so here we have the this is the transimpedance amplifier that I was telling you about earlier, which converts the current which is coming from the working electrode. So they have multiple working electrodes, working electrode 1, 2, 3 for different analytes, but they are sharing the same reference and counter electrode. So depending upon, let's say I want to monitor the glucose now, then I will switch to a certain working electrode. If I want to monitor lactate, then I will switch on another electrode. So like this I can selectively monitor certain analytes while at the same time using the same counter and reference electrode, and this goes into a TIA, transimpedance amplifier. So the input here is current, output here is voltage, and then this voltage, this is called as a multiplexer. But anyway, this voltage is again amplified. Amplified means the value is increased. So PGA stands for programmable gain amplifier. So let's say I'm having a amplifier. So let's say I am having a signal which is 10 microvolts. I want to amplify it to 100 microvolts. Then I will multiply it by 10. So the gain is 10. I want to multiply it by 1000. So 10 microvolt becomes 10 millivolts. So this is what I can choose, how much gain I want on the signal, and then or the multiplying factor, and then this voltage. So this PGA or programmable gain is required to fit within the range of the ADC. The ADC has some limitations. So it can only digitize signals between, let's say, X microvolt or X millivolt to Y millivolt. So in order to fit within this range, I have to amplify the signal, and once I amplify the signal and fit it within the range of the ADC, I can now have the analog signal converted into the digital signal, which can be understood by computers, which can be processed by computers. Okay. So if I want also, I can implement digital filters. I can have low pass filter. So let's say when we are moving fast, when we are running, so it causes, the sensor signal causes some spikes. So we can remove these spikes using the digital filters. And let's say we are sitting near electronic devices. There is some feed through or electromagnetic induction. 50 hertz we have AC signal, which is powering up our devices. So that 50 hertz might also come in. So that can be removed using filters. Clear? Okay, moving on. So we have seen how actually, so glucose and pH, these are very common biosensors that are present in labs in and around. So very common markers that we generally monitor. So I have shown you the instrumentation that is required for glucose sensing. So let's have a look at the pH sensor. So both this glucose sensor, the enzymatic glucose sensor and the pH sensor, you will see more in detail during the hands-on session. So you yourself can implement a glucose sensor. You yourself can actually implement a pH sensor as well. So this, I wanted to show you some work related to the pH sensor, and this is the last part, and after that we will take questions. So in the pH sensors, generally this is the gold standard, the glass electrode. So that is the gold standard in pH sensing. And then we can have micro spikes or micro needles. Then we have something called as ISFET. Does anybody know what is ISFET? Ion sensitive field effect transistors. So this graph actually is a very rough graph, but it is a qualitative graph. It tells us that the SFETs are very small in size, in dimension, but they are not invasive. Okay. You cannot insert it into the body as such. And then you have the glass electrode, which is very large in size, but still you cannot insert it into the body, you cannot carry it with you. So that's why we have the microneedles or microspikes or subdermal sensors, which can actually be penetrated and worn for long term monitoring, continuous monitoring. So these SFETs and glass electrodes, we cannot use it for long term continuous monitoring, but microspikes we can. So in this one, we actually use iridium oxide microelectrodes. So these iridium oxide pH electrodes are very good pH electrodes. So and easy to implement as well. So we will tell you the method how to implement it in the lab. So this is actually a gold coated microneedle sensor array, which we have functionalized it with iridium oxide. So this is the sensing mechanism. I think Sanjeev will be better able to explain this. This is a standard iridium oxide, iridium 3 to iridium 4. So this 4. So there is a transition between different oxides of iridium 4 to iridium 3, iridium 3 to iridium 4. So that is a redox. So it's a reversible reaction, and the sensitivity is around 55 to 75 millivolt per pH. And this follows, as you all know, Nernst equation. It follows the Nernst equation, and this generally, when this 75 millivolt is what we called as a super Nernstian response, a very highly sensitive device that we can have. And we have very small dimension also. The length is 100 micron of the spike, the microspike or microneedle, whatever you call it. Good response time. It changes very fast, 5 seconds. So if your pH is changing, although pH in body doesn't change that much, but this is the kind of response time that you have in pH. So we will show you this, implement the iridium oxide sensor as well in the lab, and you can see it on the hands-on session. You can get a feel of it. So what is required? So this is some work which I did in 2017 when there was no AD5940 available. So in today's scenario, I would go for AD5940, AD5941. I can immediately or directly interface the pH electrode with the platform sensing with AD5941 or AD5940. But what we need to keep in mind in pH, actually this is very important. It should have low input bias current. So what happens here is, generally when we make amplifiers, these amplifiers actually, the ideal input impedance, let's call it IZ, or let's call it ZI, let's say input impedance is infinite. So infinite means there is no current which is flowing into the terminals. Okay, so ideally we have infinite input impedance, but let's mark the word ideal. So there is always some small current which is flowing inside. Okay, so that we call it as I bias or bias current. Okay, I bias. So the input bias current should be as small as possible. There is a reason for that. I will explain as well. Very easy to understand. So when you are designing anything for like pH sensing, the input bias current should be in femtoamps. So in AD5940, if you go back to the data sheet and you can check what is the input impedance of this device and what is the input bias current that is expected for the voltage channels. Okay, so if it is in femtoamps, then it's good to use for pH. So even in picoamps also you might be able to escape, but I would say that go for femtoamps. So what happens here is, the reference electrode, the silver chloride reference electrode. So generally what we have here is, let's say this is the pH electrode. This is a very simple diagram. I am not doing the detailed. So this here you would have the reference electrode, which is AgCl, and if you have seen the AgCl reference electrode, it is a glass electrode. Okay, and there is a salt fit at the bottom. Okay, so this has very high impedance. So this AgCl electrode has very high impedance. Okay, so if there is a small current, even a small current that flows through the electrode, because of the high impedance, it gets multiplied, and you have a voltage signal, which may not be due to pH change. It may be due to this input bias current which is flowing. So what we will have here is, generally in pH sensors, I will show you in later diagram. Here we have voltage, and let's say we have time. So this is known as the OCP, open circuit potential. So the potential that we are measuring between the reference electrode and the working electrode, we call it as OCP, open circuit potential. Ideally the OCP, if you are inserting it in a buffer, let's say the pH is not changing, ideally the OCP should be like a straight line. But due to this bias current, input bias current, there is a drift, there is a small drift. So if you have very high input bias current, even in microamps or picoamps, there will be drift will be more. So femtoamps means little bit more stable. So you will have less drift, and there are some problems which arise due to drift. You can use signal processing methods or even AI driven methods also that we will see in a later lecture. You can remove these non-specific changes or variations, and you can see the nice pH signal, pH change in vivo. We will see at a later stage. So ideally you want to have very low input bias current. Why? Because I want to have low OCP drift, and the reason of having low OCP drift is that the measurement will be more accurate and stable, easier to measure. Okay. So here this is an amplifier LMP7721. So you can use this amplifier LMP7721. So again, this is, you can buy off the shelf, you can buy it online, you can implement it yourself. There are many reference designs present, you can directly use them. So it's easy to design, easy to use. Okay. So this just a brief, wanted to show you some results also about the iridium oxide sensor. So this is a micro spike that we developed, 3D printed model. First we have a 3D printed model, and this one we can also have injection. So better is to go for injection molding. So I think we used injection molding actually. So injection molding, you can have very small micro spikes like this, as you can see in the picture here, and then you put a polymer mask on top of it to make these lines or conductive contacts, and then you cover it with another polymer layer so that it doesn't interfere with the measurements, like Sanjeev was saying earlier. So you have only the spikes which are exposed, and then you have the tracks there to connect, to extract the signal. And then, so these are the different steps that are required to make the pH sensitive. So once you have made these electrodes, once you have sputtered it with gold, because a polymer is non-conductive, you can actually gold sputtering also gives a uniform layer, and then you can functionalize the gold layer with iridium oxide, and then you can calibrate it. So this is the process of oxidation, or you can say how you can electroplate it, or you can I don't know if this is the right terminology. So generally we use cyclic voltammetry to create a layer of iridium oxide on top of the microneedles, and then this is the nice curve that we have been seeing. This is the CV curve that you would see for functionalizing the iridium oxide. So which tells us that the nice the layer of iridium oxide has formed on top of it. So and then of course you can calibrate it. You can use different pH buffers to calibrate your sensor and see if your sensor has a linear response. If it is linear, what is the range, linear range, what is the sensitivity? So sensitivity is around 0.075 millivolts per pH. Okay, so for every pH change, 1 unit of pH change, your potential will change by 0.075. Sorry, this is volts. This is volts, or in other words, you can say this is actually equal to 75 millivolts per pH. Okay, so for every unit pH change, you would have 75 millivolt change in voltage. Okay. Okay, and linearity is important for the sensor, so that you can have a constant sensitivity. If the sensor is not linear, then your sensitivity will change and it's hard to estimate. Okay. Okay, now this is actually at that time there was some experiment which was going on on hearts, excised hearts, ex vivo heart. So where we wanted to see if using these pH sensors we are able to check, let's say if there is ischemia, that means oxygen supply is restricted, pH will change in the heart or not. So this is a male Vista rat heart which has been excised, and the microneedles have been implanted on it, and this is the kind of histopathology after you have implanted and you have taken out the microneedle. You want to see what is the damage on the tissue that has been done, or what is whether it has really penetrated or not. So these are some imaging. So overall, so we tried to validate these microneedles using in this application where you induce heart attack or ischemia, and then you try to revive the heart again, so and see if there is any change in pH or not. So this shows us, this result here shows us that, you know, if you look at the pre-impalement ECG and the post-impalement, there is not much of a difference between pre and post. That means the heart is not damaged because of implantation. Okay, and this is where we are inducing the ischemia or heart attack, you can say, by cutting off the oxygen. So this is the kind of drift that I told you about earlier, and this actually had this LMP amplifier that I had shown you. There is still a little bit of drift present in this in this recording. So this is the OCP drift. This is the OCP drift. It happens due to very small current that flows into the amplifiers, pH amplifiers. It can be femtoamps, but you see that there is a drift. So what you do is, if you look at the dotted line, you can estimate the drift, linear drift, and then subtract it from the signal, so you get a flat response. That's how we do it, and that's how you can actually remove the OCP drift, and then you can see the nice peaks in the signal. I'll show you in the next slide. Is there. So yeah, so these are, so we had around, if I am not, so we had around 7 microneedles on the array, and you can individually monitor them using these, you know, so here you are actually inducing the ischemia, pH goes down, reperfusion, pH increases, then goes down, increases. In this way, it tells us that you can reliably monitor the pH in tissues. So that was the objective of the study, and then you see that there is little bit of drift also. Even after drift removal, there is slight drift is still present. So it's very hard to remove the OCP drift. So the absolute value, if you are calculating the absolute value, you have to be very careful about the drift. And this we combined it in a nice package PCB. So this is a flexible PCB cable, which you may have seen earlier, FPC cable or flexible PCB cable, and it's connected to the electronics, battery, and everything is there. So now, just towards the end, we are almost going towards the end. So here, one of the challenges in continuous monitoring is the degradation in sensitivity due to biofouling. Once you implant the sensor, you see, so this is actually this, if you look at the right hand side plots, this is a CGM sensor. You know, initially it's a very vague, I mean, it's only one off experiment, but it gives you an idea, a qualitative idea. So you see that the blood glucose, the finger stick reading and the CGM reading are more or less matching, but as you move on, there is a gap between the capillary blood that you are drawing from the finger prick and the measurement that is done in the CGM sensor. So this is with increasing number of days. So that means there is some degradation on the sensor, which causes the sensor value to vary from the blood glucose value. And then of course this is the linearity plot. So ideally they should overlap, but they are diverging as you go, you know, day wise. So this, you know, this variation is still acceptable within the FDA approved guidelines. So that's why these sensors are still being used up to 14 days. They are still within the range, but as an engineer, we try to think, can we solve this? Can we close this gap? So yeah, there were some sensors which were present in the market where they actually ask the user to calibrate the sensor daily, twice. So every 12 hours, you can take a finger prick reading, and they have an app where you can enter this finger prick reading, and whatever reading they are getting from the CGM, they try to close the gap. They try to, so that is a 2-point calibration that they try to do it. But of course it is inconvenient. If you are using a sensor, then what is the point of taking the blood glucose reading again? So ideally, so what people nowadays have, and we'll show you some sensors also in the lab. So they call it factory calibrated sensors. They have already calibrated it, and they know how much the sensor degradation will happen, whether it is within the range, FDA approved range or not. So, but ideally what we want is, we want these readings to be as close as possible to each other. Okay. So with that application in mind, we actually tried to see if we can do it. So this is one of our publications from our group, where actually we tried to probe the surface of the sensor using electrochemical impedance spectroscopy, and then whatever parameters you are getting from the EIS, you prepare a data set and link it to the sensitivity, and then you can actually attempt some sort of a prediction with respect to days. So you can actually say that okay, at day 11 or day 10 what would be the sensitivity based on the EIS measurement of the sensor. So this is a very early proof of concept study that we did, which demonstrated that yes, there is possibility. Of course, you can expand it by going more in depth, try to do in vivo results and all these things, which we are trying. This is another attempt. So that was the glucose sensor, enzymatic glucose sensor. This is pH sensor. Here we tried to coat it with PVA coating, which is an biofouling resistant coating, and then you look at the impedance, you probe the impedance and try to find out. So we found out that okay, with PVA coated, whether it is PVA coated or PVA not coated, there is some link between the sensitivity and the double layer capacitance. So if when we have, if there is a deposition of biofoulants on the sensor surface, naturally your double layer capacitance will increase, and then there is a link with the sensitivity. So these kind of modeling relationships we tried to make so that we can actually predict the sensor sensitivity day wise without having to do the finger prick reading. So that's all, almost towards the end. So this is a platform that we have developed in the lab, low cost device, very easy to make, and we have integrated with the electronics. We can show you also later on. And this is the high density microneedle based platform, which Sanjeev is an expert in that. So we also tried to do some microneedle development, which we have made, but yeah, it's not perfect as yet. So this will give us, so you can say this is high density monitoring, so of the analytes. So this is kind of low density. So the more number of higher the density, better reading you will get, better surface area is there, so more accurate will be the reading. So that's all from my side. I mean, if you have any questions, you can ask. So overall we covered the amperometry and potentiometry, what are the requirements from an instrumentation perspective, and what is the latest instrument that you can use, latest platform, which is AD5940, AD5941 that you can use. Yeah.
Sir, like you said, the sensor degrade over time. So which one should be easier for a person to develop it for increasing its shelf life, or to make it more cost effective, like in today's generation?
So I would say making it cost effective will be better, because what we got as user feedback, people who have actually, we did a small survey within people who are using CGM sensors. So they don't like to, they don't like the device being attached with them for very long amount of time. So it's more important that we, if the sensor is cheap, they can replace it frequently. So it's more of a comfort level. So people want to use it maximum for 1 week to 10 days. And they don't want it to be attached for a very long time. They feel a little bit uncomfortable sleeping and other things. So I would say, if you ask me, my personal opinion is we should aim for cost effectiveness, so that you can have more number of sensors replaced easily, rather than having one sensor for 1 month. So right now these sensors cost around 5,000, these CGM sensors. So if somebody is using it 2 times in a month, so the recommended use is 14 days. So every 28 days you would require 2 sensors, so that is 10,000 cost. Now imagine if you reduce the cost by 10 times, so let's say 500 or even 1,000, and you can have 10 sensors within the same budget, and it may be more comfortable, better to read, it will be more accurate because you are replacing it frequently, and there will be less engineering stress on the sensor as such. The reason all sensors are not same, why we did this prediction sensor sensitivity prediction, because you see we have a glucose sensor, it may not react at the same way when you insert some other kind of sensor. So it depends on how what is the sensor surface that you are using. So the body might have a much more stringent reaction to sensors to different surfaces. Okay, so depending upon the it also depends on depends on the type of surface that you are using. Let's say the body reacts more quickly to a certain type of sensing layer, then you would require this sensor prediction within 7 days also. Okay, so from a glucose sensor perspective, my personal opinion is it will be good to focus on reducing the cost of the sensor so that people can use it more frequently, and reducing the weight of the sensor, make it more like a patch, like a band-aid. Many of us have used this band-aid. When you have a cut, we use a band-aid. Something of that weight will be really nice. You don't even feel it. So around we have sensors, so you can actually feel the sensor after the session. You can have a look how what is the weight of the sensor and how it feels. You can have a look. Sir. Yeah. Yeah. Yes. Yeah. Yeah. Iridium oxide. Yeah. Yeah. So the sensing mechanism is different. So here the equilibrium reaction is different. So it is this iridium 3 to iridium 4. I'll show you. Just 1 minute. Let me just go back to that slide. So this is this. So this reaction is different in a glass electrode. So only this would be different in a glass electrode. The reaction sensing reaction is different. Yeah.
Okay, so the mechanism is totally different.
Mechanism is different. Yeah.
Totally different.
Yeah.
And is it like because of that actually you are getting this sensitivity somewhere, like because normal
Yes.
glass electrode we have read like somewhere 59, like
Yes,
theoretically like 59 millivolt per pH.
Yes. So it is because of this. Actually, I have shown you one interface reaction. So there are 3 possible interface reactions actually happening. So
Okay.
This is one of them. So that is why the sensitivity is varying from 55 to 75. So depending upon what type of reaction is happening, it will be different. So people have so when you are coating iridium oxide layers on the sensor surface, there are many different protocols. It depends on the protocol also. So different protocols will give you different type of sensitivity. So in some protocols you will get which is close to glass electrode around 50, 55, and in some protocols you will have a super inertial sensitivity which is around 70, 75. So it depends on the protocol.
And then application point of view, like where you cannot use glass electrode, there you can use this.
Exactly, yeah. Where we cannot use glass electrode is the gold standard. So even if we make these electrodes, we always validate it with the glass electrode. So whether we are getting the same reading with the pH electrode that we have in the lab and the microspike that we have developed. So that comparison is always there. So if you make, let's say, a new array and you are trying to publish it, then you have to show the comparison with a glass electrode to convince the reviewers. So that is always there. The only application is, let's say we cannot penetrate the glass electrode, there we use the iridium oxide electrodes for penetration.
Okay.
So
these glass electrodes are not in micro and semi-micro, I mean, no. Okay.
And I have seen some capillary type of structure glass electrode also there, but they are easy, they break very easily. So I remember using, we made some very thin capillary based glass electrodes for animal experiments, but they are not reliable, they break very easily. That is the when you penetrate, when you try to take it out, sometimes it breaks, the tip breaks and stays inside the body.
Okay. So another query regarding this chip you told is something like totally new for me at least.
Sir, this one, right?
Completely.
Yeah.
Yeah. So Because we have a big this potentiostat.
Yes.
My question here, can you use it for voltammetry?
Yes,
I mean,
yes.
you can change also the potential with
Yes,
time.
yeah, you can use it for voltammetry also. So they have some, they have functionality here. So this waveform generator, so this waveform generator actually you can use it for voltammetry also. So let's say you want a triangular waveform for voltammetry, so you can program that.
Oh, okay.
Yeah.
And then
So
the paper you showed that nature,
Yeah.
like three things it was like analyzing.
Yes. Yes.
Like it's like not in the same simultaneously. It
No,
was
not
measured?
simultaneously. No.
You have
So
to stop.
yeah, so they have this switch. So this is a switch here. So whenever they require a certain analyte, they will turn on that switch or select it. And because what happens is they are actually sharing the counter electrode and reference electrode. So you
But
cannot
three
have
different
simultaneous.
working electrode you told, right?
Huh?
Three different
Working electrodes and one reference and one counter. So they cannot use all three working electrodes with the same reference and counter.
Okay.
So they are forced to use this. So if you want simultaneous measurement, you might have to have separate
Three reference,
three reference, exactly.
Okay, maybe.
Yeah.
Thank you. And probably this LDO, like yesterday you
yes,
were talking about,
So
today.
I will show you. It's there in this block diagram also.
Yeah.
So here,
Maybe another one somewhere it was there. This is a total detail block diagram.
yeah. So you
Maybe
see, here, sir, look at this
Yeah.
LDO. So it generates a constant voltage. Whenever you require constant voltage, so this will be operated. You can operate it with a USB, let's say, or a battery. Battery generally is 3.3 volts. So this will convert your 3.3 volts to a constant voltage LDO. So one output will be 1.82 volts. In that way you can do it.
Thank you.
Sir, I have also a small question. In that continuous glucose monitors,
Yes.
The reduction potential was set at 650 millivolt.
Yes.
But if we go for the literatures,
Yeah.
the FAT moiety in the glucose oxidase or for even glucose also, they are very, they are close to zero. Like for glucose oxidase, it's 80 millivolt, and for glucose, it is 420.
Yeah.
Then why is it set for 650 millivolt?
So actually what happens is, you cannot use the enzymatic electrode GOX directly because there is problem of interference. So like we discussed last time, acetaminophen, it's an interferent, ascorbate, it's an interferent. So what people do is they use some layers. There is some layer called naphion, you must have heard, it's a polymer naphion. So they do these changes to the surface to enable to avoid the oxidation potential to be same as the interference. So that is the reason why you have different voltages, okay, because of the changes in. So ideally so once you make a sensor and you functionalize it with naphion or some other kind of polymer, it shifts, the potential shifts. So that is the reason.
Thank you so much, sir, for this informative presentation. And sir, I want to know that you have talked about the artificial intelligence and machine learning, and you have just said about the accuracy and in comparing the things. And as we are going towards the agentic AIs and generative AI and artificial general intelligence, so sir, how these things will change the pace of the researches which is right now ongoing, and how it will help in personal medications?
Okay, sure. So your question is a little bit broad, so I'll try to make it specific to this topic. Let's focus on generative AI. So I will show you in another lecture. What happens is when we use these CGM sensors, Sanjeev, you might know also. So you have also shown sometimes what happens is you might have missing data points, right? So if you are using a Dexcom sensor which has a Bluetooth device, let's say that Bluetooth is connected to my mobile phone. I have left the mobile phone over there somewhere out of range and I am moving about. So there is a drop of data points are not present, they are absent. Okay, so you can use generative AI to generate the missing data points. So once you use that missing data points, then you are safe with your AI and the decision making. You cannot make any decision without data. So you require data. So if you want the data to be as close as possible to the glycemic profile of an individual, then you can use Gen AI. So you can use GANs, we have done that also, to replace the missing data points and then use the decision. So that is one answer to. Other than that, you can see there are many other applications of Gen AI. For example, many people have tried to develop an LLM for diabetes. Let's say somebody is having some issue with diabetes, or they want to ask a general query. So they can ask an LLM which has been trained on these applications, and LLM can, so like a chat GPT for diabetic patients, so it can answer specific queries. Let's say you want to ask what should I take insulin or not, or maybe what is my current glucose level, should I take a walk or not. Sometimes in type 1 patients, one of the concern is physical activity. So if they do very rigorous physical activity, then glucose level falls, then the insulin dose also changes. So if you cannot have the insulin dose which is same for without physical activity and with physical activity, because you might require less insulin to avoid hypoglycemia. So in that scenario, actually LLMs, which are part of generative AI, they can answer queries. You don't have to call your doctor and ask as such. At least for something quick query you can ask. Then if you want to verify, you can ask a doctor. So these are some applications of Gen AI in diabetes.
So I have one question. You talked about this instrumentation. So many a times during this electrochemical sensing, because of some other fluctuations happens, because this is oxidation reduction reaction, so may not be very smooth because of the diffusion problem or mass transfer limitation. So can this instrumentation can handle those fluctuations, or it need to be cured or corrected with the algorithm only?
No, there are so here we have filters here.
Okay.
See, digital filters. You can use some basic noise removal. You can use digital filters to do that. Let's say you have a sudden spike due to movement, or let's say you fell down or you moved your hand and there is a sudden spike. So you can use a digital filter to remove that spike.
So instrument can
instrument
take care
can do
of
it. You have to program it. So this is programmable. So it's like a microcontroller. A microcontroller generally has mostly an ADC, which is an analog component. Rest are digital. So this is a nice platform because it combines both analog and digital together. You can program it also if you want. So you can use many different ways to program it. So these GPIOs you can use to program certain filters.
So I think there's no more questions. So we can conclude this session.